Okay, so good evening and welcome back to this problem solving session for the NPTEL course Foundation Engineering. So, for those who are new to this session, myself Shivshankar Nandi. So, I am pursuing my PhD in Civil Engineering at IIT Kharagpur, and I am one of the TAs for this course. So, this is a short introduction of me. Okay, so in the last week, we had discussed about the fundamentals of soil mechanics, and subsequently we had solved a couple of problems uh, regarding this three-phase relationship, then compaction, consolidation, determination of effective stress, and I think shear strength, and two or three problems regarding the standard penetration test. So those who have gone through the lectures of week 2, so you may know that in this week we have covered broadly this topic called indirect in situ methods of soil exploration. So in the last week we had seen there are three types of methods by which we can conduct the soil exploration program, and those are the first one direct, then semi-direct, and lastly the indirect methods. So under direct methods we have seen the example of open test pit. Then for semi-direct method, different types of borings, wash boring, percussion drilling, then this rotary drilling, and so on. And finally, under this indirect in situ methods, we just started the standard penetration test. So in this week we have seen a few more penetration tests, and those are cone penetration test, pressure meter test, dilatometer test, and wind shear test, in addition to the standard penetration test. Okay, so this cone penetration test can be further divided into two categories. As you know that these two categories are static cone penetration test and dynamic cone penetration test, DCPT. Okay, in short. Now, what are the topics which we have learned regarding this penetration test? So broadly we can say that we have learned the applicability of this test, the standard procedure, and different corrections if required, and finally the derived parameters or correlations with the basic properties of soil, okay, which will be requiring for the design, or design in the sense that determining the bearing capacity or settlement calculation. Okay, so we'll see in the due course of this course. Now in the next part of this week we have discussed, or we have learned about two types of samples. So what are those two types of samples? Can anyone please explain a little bit about those two types of samples? Okay, so these two types of samples are disturbed and undisturbed, and the definition you can derive from the terminology itself. Disturbed in the sense when the structure, original structure of the sample which we are basically extracting from the field, so the original structure is basically not preserved. Okay, so that kind of sample is called disturbed, and in the case of undisturbed it is the opposite scenario. So the original structure of the soil as well as few other important properties are getting preserved. Okay, So these are the definition of disturbed and undisturbed samples, and I think you should know about the necessity, or about the what I can say, that the application of these two samples. Okay, so for example, suppose you cannot use this disturbed sample for determining shear strength, consolidation, or hydraulic conductivity of soil. So for determination of these properties, you should require the undisturbed sample. On the other hand, for determining the grain size distribution or Atterberg limits or classifying the soil, you can use disturbed sample. Okay, so disturbed sample can be used for determining grain size distribution, Atterberg limits, and classifying the soil sample. Whether this undisturbed sample is required for determining these shear strength properties, consolidation parameters, and hydraulic conductivity. Okay, so now the next topic is how we can basically extract these samples, disturbed and undisturbed. So two types of samples we have seen, thick walled and thin walled. And what are the parameters based on which we can say, okay, this sampler will give you this type of samples. So can you please say me what are those parameters or indices based on which we can say that thick walled sampler will give you disturbed or undisturbed? What are those indices? Okay, so I think all of you know about these parameters. So these are nothing but area ratio, then inside clearance, outside clearance, then recovery ratio, and so on. Okay, so these are the few indices or parameters of the samplers. Based on the value or based on these parameters, we can conclude whether this type of samplers will yield this type of samples. Okay, okay, and later on we have learned, or we have seen a few specifications regarding boring. So for a project, so first you should go for some geotechnical investigation or geotechnical exploration. Now when you will deal with such aspect in real life, so what should be the numbers of boring, what should be the spacing between two boreholes, and depth of boring. So you should know about these concepts, and you should be having an in-depth knowledge of this concept. Otherwise you will not basically do your job, you will not be able to do your job in a proper manner or proper way. Okay, so these things also we have learned from this week. And lastly, we have learned 3 geophysical exploration programs like seismic reflection survey, seismic refraction survey, and seismic crossing survey. Okay, so in this week, through some selective numerical problems, we'll basically try to comprehend these aspects in a more detailed manner. Okay, okay, so first we'll start our today's session with this problem, and this problem is related to the correction of field SPT value, SPT n value, and as per IS code, IS 2131-1981. So let me read the problem statement first. So the field n value in a deposit of fully submerged sand was 40 at a depth of 6 meters. The average saturated unit weight of the soil is 19 kilonewton per meter cube. So calculate the corrected n value as per IS 2131-1981. Now, please tell me, what are the two types of corrections which are prescribed by this IS standard? So this is the measured SPT N value at the field, and it's measured at a depth of 6 meters. And the average saturated unit weight of the soil is 19 kilograms per meter. Now first let me know what are the two corrections which are prescribed by this Indian standard. I think you must have known, na? Okay, I am assuming that you know. Okay, so first of all, this corrections prescribed by Indian standard are overburden correction, and secondly, dilatancy correction. Okay. Now we'll discuss these corrections one by one. So first, for overburden correction, you need to multiply one factor with the field SPT N value so that you can get the corrected N value considering the overburden correction, and this Cn is nothing but the correction factor. Now coming to the next part, that is the dilatancy correction. This correction is basically applicable for some scenarios. Now what are those scenarios? So first of all, the soil deposit which you are dealing, that should be submerged or fully saturated fine silty soil mass or fine sand. Okay, so this is one condition, and the next condition is that after correcting for the overburden pressure, this corrected SPT N value should be greater than 50. Now if these two conditions or criteria meet, then you can go for dilatancy correction. There is a need for dilatancy correction. Otherwise, there is no need to go for dilatancy correction. Okay. Now, how this correction will look like? So, N double prime would be 15 plus half N prime minus 50. This N prime denotes the corrected SPT N value after applying the overburden correction. Okay, and this N double prime indicates it's basically it has taken care of both the corrections, overburden and dilatancy. And please keep in mind that this dilatancy correction is only required when the soil deposit is submerged or fully saturated fine sand, and that this corrected SPT value after overburden correction is greater than 15. Otherwise, there is no need. Okay. Now, let me know why these corrections are required. What is the physical significance of this type of corrections? Why we are basically imparting, or we are basically considering this overburden correction, dilatancy correction for submerged fine sand, or this N prime value greater than 15? Do you know? Okay, though it's not needed for solving this problem, still I am explaining a little bit about the necessity of this type of corrections. Okay, now you should know, or you may know, that this SPT test is basically conducted for cohesionless soil. Okay, though you can conduct this SPT test for cohesive soil, but it's basically more pertinent in the case of cohesionless soil. Now, from the basic concept of shear strength, suppose the relative density of two cohesionless soil samples or two soil samples are same. Now, if you conduct the shear strength for these two soil samples at different confining pressure, now what will you observe? The result or response which you will be expecting, that will be similar kind of response you will be expecting, or different? Though the relative density is same or similar for both the samples. So you are just varying the confining pressure in the shear strength test. So will you be expecting the similar kind of behavior, or there will be a discrepancy in the response? What do you expect? So you will be basically expecting a different behavior for both the samples. So first of all, as you increase the confining pressure, so it will basically give you more resistance. Okay, so more deviatoric stress you will be observing. So similarly, when you are basically constructing a borehole in the field, so as you are basically going down below, so suppose you are basically determine the SPT at 6 meter. Now someone can basically determine the SPT at 8 meter. So as you basically go down below from the ground surface, so due to the increase in the overburden pressure, so overburden in the sense the unit weight multiplied by the depth. So the depth which you are considering, that depth multiplied by the unit weight of the sample will give you the overburden. Okay, though effective overburden is a different scenario that we'll discuss. So as you go down from the ground surface, so your overburden will increase, and overburden increasing, that means the confining pressure also increasing. So therefore, to maintain a uniformity in the response, means this n value will be later on correlated relative density or consistency of the cohesionless soil. So to maintain a uniformity, you need to implement, or you need to consider or apply this kind of overburden correction. Okay, overburden stress. Now coming to the next part, dilatancy. Why dilatancy is needed? Now for applying the dilatancy, first you have to meet these two criteria, that it should be saturated fine sand and the n prime should be greater than 15. Now what does it indicate that n prime greater than 15? So n prime greater than 15, it indicates that the soil sample which you are dealing with, that is somehow dense in nature. For example, dense sand. Now this SPT test is basically quick. So you are basically applying the loading in a very fast manner, rapid manner. So if you basically take the analogy of shear strength, the response of sample in the shear strength test, so what you will get? So first of all, this sample is saturated fine sand, and then this n prime greater than 15 is basically indicating it's dense in nature. Now what would be the behavior for rapid loading under these conditions, or considering these conditions? Rapid loading, it will basically give you an idea of undrained condition. Since this is saturated, so the pores are basically completely filled with water. So when you will be applying the load in a fast manner, so there will be no chance of dissipation of the excess pore water pressure which will be induced due to the application of this load. So that means this undrained condition will prevail. Now what is the response of this kind of dense sand under undrained condition in shearing? What is the response? So if you plot this pore water pressure, excess pore water pressure versus axial strain, So it is basically from the very basic soil mechanics. Okay, so this is for loose sand or normally consolidated soil, and there is another curve in this plot, something like this. So this is for dense sand or over consolidated soil. So this is plus, this is plus, this is minus. So that means you may get negative pore water pressure inside the soil sample in this kind of soil. Saturated, fine, dense sand, N prime. We are assuming that N prime greater than 15, it will somehow indicate the sand is basically dense in nature. Now due to this application of load in a very fast or rapid manner, there will be a chance of generation of excess negative pore water pressure. Now whenever you will be getting the excess negative pore water pressure, now your strength will increase or decrease, your shear strength will increase or decrease. It will increase, na, because the effective stress itself is total stress minus pore water pressure, and from the Moore Coulomb criteria or Moore Coulomb envelope, the shear strength is nothing but C prime plus sigma n prime tan phi prime. So for sand, though C prime part is 0 and sigma n prime is nothing but the normal stress. So this is suppose sigma n prime, sigma minus C dot. So that means this effective stress is increasing, so you will be getting more strength. Okay, so that's how we are basically overestimating the response as we can get in the actual scenario. So we are basically here overestimating due to these conditions. The first one, saturated fine sand, and the next one is N prime greater than 15. So that's why this dilatancy correction is required. So I hope you have understood. Okay, now we'll go back to the problem solving part. Now how we can determine the CN factor? So this is the overburden stress correction factor, CN, and this N is nothing but this 40. Okay, the measured SPT N value in the field. So how we can get this CN? How we can get this CN? This correction factor. So for this correction factor, this is the correction factor. Due to overburden stress, we have to refer one chart which is given by the standard, Indian standard. Now this is the chart. Okay, so this chart, I think all of you are familiar with this chart. Okay, so it's given in the lecture materials itself. Now as you can see in the slide, so in the y-axis, it's effective vertical overburden pressure in ton per meter square, and in the x-axis, this is the correction factor CN. So to determine CN, we have to first calculate the effective vertical overburden pressure at the concerned depth. So here the concerned depth is 6 meter. So at 6 meter, we have to calculate the effective overburden pressure. Now how we can calculate? So it's very simple. It's total stress minus the pore water pressure, and the total stress would be nothing but gamma sat minus gamma sat multiplied by the depth Z, and then minus pore water pressure, so gamma W into Z. So here, since the sample or soil is fully, the soil deposit is fully submerged, so that means you can assume that the water table is at the location, means is locating at the ground surface itself. Okay, so gamma sat is given to you 19, Z value is 6, then gamma w you can take it as 10 and z is again 6. Now what would be this value? So 19 into 6 minus 10 into 6. So this value would be 54 kilonewton per meter square. But you need to calculate this value in terms of ton per meter square. So you have to divide it by 10. Okay. Then only you can get the expected result or required or desired result. So now you have computed the effective vertical overburden pressure at the concerned depth of 6 meter. So now you can easily determine the correction factor Cn for overburden stress correction. So we'll refer this chart. So this is starting from 0 here. Okay. So 0 here. So 0, 10. So in between it's 5. So somewhere here it will be 5.4. So I am basically drawing a horizontal line marking effective vertical overburden pressure as 5.4. Sorry. Okay, so my drawing is not too good still. Okay. So accordingly, you can take this correction factor Cn as 1.2. Okay, so I am erasing this part. Okay, so you can take this as the correction factor. So obviously Cn is your 1.2. So that means the corrected SPT n value, it would be 1.2 multiplied by the measured or field SPT n value, that is 40. That means 48. Now coming to the next part, that is the latency correction. So the soil is submerged sand. So this first condition is fulfilled. Now what about the second condition? It is also fulfilled, since this 48, this n prime value is 48 and it's greater than 15. So both the criteria are fulfilled. So therefore there is a need for dilatancy correction too. Okay. So what about the dilatancy correction then? So it would be 15 plus half 48 minus 15. Therefore 15 plus 48 minus 15 means 23 divided by 2. That means 26.5. Sorry, it's 33. So 15 plus 33 by 2. Okay, so 31.5. Please correct me, okay, if I am wrong. So 31.5. So you have to report in integer. So you can take it. 31 is the correction considering both overburden and dilatancy. So any doubt so far? Any confusion for problem 1? Otherwise we can proceed further. So this is the way you have to incorporate the correction which is specified by Indian standard IS 2131, overburden and dilatancy. So overburden is basically for all, whatever may be the scenario, you have to apply overburden first. Now if these two conditions are only met, then you have to go for dilatancy, otherwise not. Okay. Now coming to problem 2. It's regarding the same topic, the correction of SPT n value, but as per the ASTM standard. ASTM D1586. So while performing SPT in a submerged sand deposit, the flow counts at a depth of 15 meter were 15, 18, 20 respectively. Other data were given as year 80, length of the rod 11 meter, the sampler is without liner, the correction factor for borehole diameter is 1.05 and the submerged density is 7.93 kilonewton per meter cube. State the consistency of the soil. Now, what do you understand by consistency of soil, especially for questionless soil, since this is submerged sand deposit? What do you mean by the consistency of a questionless soil and how it's represented? So again, it's basically from the very basic fundamentals of soil mechanics. So for determining the consistency, first you have to know the relative density of the sand. Now what is relative density? So relative density is nothing but E max minus E divided by E max minus E minimum. Now this value is less than 15, then it's very loose, then 15 to 35 loose, 35 to 65 medium, something like that. We can basically classify the consistency of the soil based on the value of relative density. Now this type of data is not available with us. So what we can do now? So we can basically take the help of some correlation with the relative density, correlation between relative density and the SPT value. Okay, so this is one application of the SPT value for questionless soil. So for that, we have to first determine the field N value, then the corrected SPT N value, and then we have to correlate this SPT N value with the relative density of the soil, and then we have to state what is the consistency of the soil. So these are the few basic steps to answer this question. Okay, so you may come across this type of table in the lecture contents, in the lecture materials which are uploaded in week 2. Okay, so in the first column, this is n prime 60, and please keep in mind that this n prime 60 is not accounting for the correction due to overburden. Okay, so we'll come what is n prime 60 according to ASTM D1586. Now from this table you can easily see that if this n value, n prime 60 value is in between 0 to 4, then dr would be in between 0 to 15. Accordingly, you can say the consistency of the soil is very loose. So consistency in the sense the degree of denseness. So similarly, if it is in between 4 to 10, relative density would be 15 to 35 and consistency would be loose. Okay, so therefore we need to know about the n prime 60 value, about the calculation of n prime 60 value from the given data like the field SPT N blows, or still it's not directly given. Okay, so instead of that, the flow counts at a depth of 15 meter are given like 15, 18, 20. Okay, for consecutive 150 mm penetration, and you know that the SPT N value, field N value, is defined as the summation of the number of blow or the blow counts required for the last two 150 mm penetration, because the first one is basically neglected due to setting error or setting right. Okay, so therefore in this problem, or for this problem, we have to add these two blow counts, 18 and 20. So 38 is the SPT N value. Now we'll come to this topic, n prime 60. So n prime 60 again, it's the corrected SPT N value, and please keep in mind that SPT N value is always standardized to some energy ratio. For example, this 60, the suffix 60 will basically denote that standardized energy ratio value. So where the standardized energy ratio value is 60%. Okay. Now what are those corrections? So the corrections are, first of all, overburden correction, then the measured SPT value, then there are 4 more correction factors like eta 1, eta 2, eta 3 and eta 4. And please remember that these corrections are basically in accordance with ASTM D1586. Okay. So this CN part will not consider for this problem. Why? Because it's not needed. Okay, it's not needed. So you need not to correct for the overburden for stating the consistency of the soil sample. Okay. Okay. So anyhow, the CN you can determine from this equation 95.76 P0 prime whole to the power half, and this is given by Liao and Whitman, I hope in 1986. Okay, so if needed, you can also determine the CN factor as per ASTM D1586, and here P0 prime is nothing but the effective overburden pressure at the required depth. Okay, so this is nothing but the effective overburden pressure. Now, what about other correction factors like eta 1, eta 2, eta 3, eta 4? So for that you have to go for some charts which are also given in the lecture materials. Okay, so first of all, this eta 1 corresponds to correction due to hammer efficiency. Then eta 2 corresponds to correction due to rod length, eta 3 sampler correction, and eta 4 borehole diameter correction. Now one by one we'll calculate all these correction factors. So first of all, we'll calculate, or we'll start the calculation with the hammer efficiency correction factor. So hammer efficiency correction factor you can calculate from the ratio of these two, ER divided by ERB. Now what is ER? What is ER? ER is nothing but the energy ratio, and this ERB, this is the standardized energy ratio. So ER is the energy ratio for a particular hammer which you are using in the investigation, and ERB is the standardized energy ratio. So for this case, this ERB is nothing but 60%. Okay, so this suffix 16 denotes this condition that ERB equals to 60%. Now what about ER? ER, it will be 45 to 67 for do not hammer. If you use do not hammer, it will be in between 45 to 67, and if you use safety hammer, it will be like this. But for this problem, it's directly given to you, so it's 80%. Okay, so therefore you can easily calculate this hammer efficiency correction factor. Here I am calculating, so 80 divided by 60. Okay, so that means 4 by 3, so 1.3. So this will be the hammer efficiency correction factor. Now coming to rod length. So for different rod length you will be having different correction factor, 0 to 4 meter, 4 to 6 meter, 6 to 10 and greater than 10. Now since the given rod length is 11 meter and it falls in this category, okay, so the correction factor would be 1. Similarly, for different sampler condition, you will be having different correction factor, without liner, with liner and with liner, to soil deposit condition, dense sand, clay and loose sand. So since the soil sampler used is without liner, so therefore again the correction factor for sampler would be 1. Now coming to the last correction factor, that is correction factor due to borehole. Again you need not to go for calculate because it's directly given to you. it's 1.05. So therefore I am summarizing all these correction factors related to this problem. So first of all, eta 1 it's 1.33, then eta 2 1, eta 3 again it's 1, and finally eta 4 it's given as 1.05. okay, if it's not given, then you can determine from this table depending on the hole diameter, 60 to 120 mm, 150 mm and 200 mm. Okay, so now we'll substitute these values in this equation. So n prime 60, this is without overburden correction. So first of all, a measured SPT value is 38, then 1.33, this is the hammer efficiency correction factor, then rod length correction factor, then sampler correction factor and borehole diameter correction factor. Okay, so what is the value you are getting then? So it would be 53.1, okay, or 53. Now we'll go back to the past chart, that SPT correlations in granular soil. So the corrected SPT value without accounting for overburden correction, we are getting as 51. So 51 in the sense, which row? This row, greater than 50. Okay, so that means the relative density of the soil deposit would be in between 85 to 100, and therefore it is very dense. Okay, so it's very dense. So we can say the DR value, so it indicates that the DR value would be in between 85 to 100%, and consistency would be very consistent. Any problem up to this part? Okay, so if not, then we'll proceed further, and this is our problem 3. So problem 3 states that in a submerged sand deposit SCPT was performed at a depth of 8 meters. The cone tip resistance was found to be 580 kPa. Calculate the friction angle, where the saturated unit weight is 17 kilonewton per meter cube, unit weight of water is 10 kilonewton per meter cube. So again, this is an example for correlation of the SCPT test data with the friction angle of the drilled soil deposit. Okay, the soil deposit we are dealing with. So this is an example how we can correlate the cone tip resistance which we are getting from conducting the SCPT test with the friction angle of the sand deposit. So how we can correlate? Can you please remember any equation, any table, anything like that? Okay, so again, this is basically taken from this weekly lecture material. So in sand, you can basically correlate the cone tip resistance with the friction angle of the sand deposit in this manner, and this is basically given by Pulhaoi and Maine 1990. Okay, so where phi is the friction angle, QC is the cone resistance, and sigma P prime or P0 prime is the vertical effective overburden pressure or stress. So this is the equation, phi equals to tan inverse 0.1 plus 0.38 log of QC divided by sigma B prime. So just you need to know QC, which is the cone tip resistance, and this is 580 kPa for this problem. And secondly, you need to know about the overburden pressure, vertical effective overburden pressure at that depth. Okay, vertical effective overburden pressure. Okay, so the same calculation you have to go for. So first total stress, then pore water pressure. Okay, so I am directly calculating here. So gamma submerged, since this is the basically this equals to gamma sat minus gamma w. So 17 minus 10 multiplied by the depth. So 8. So 7 into 8, that means 56 kPa. Okay. So we know QC, we know sigma B prime. So pi we can easily calculate from this given equation. So tan inverse 0.1 plus 0.38 log of QC is 580 divided by, okay, so log of 580 divided by 56 multiplied by 0.38 plus 0.1, tan inverse of that will give you 25.9. Okay, so again this is an example by which we can understand how we can correlate the SCPT test data with the friction angle, shear strength parameters of soil. So here we are basically taking the reference of sand deposit, that is cohesionless soil. Similarly, we can utilize the cone tip resistance data for the cohesive soil also, for determining the undrained cohesion of cohesive soil. Okay, so please check. Okay, now before proceeding further, please let me know what is the major drawback of this SCPT with respect to SPT, and again what is the plus point of this SCPT as compared to SPT. Can you please identify? Or in other words, we can say what are the differences between SCPT and SPT. SCPT means static cone penetration test and SPT means standard penetration test. So what are the differences? In terms of merit and demerit. Okay, so first of all, in case of SCPT, you cannot extract the sample. So this is one drawback of this kind of test. Okay, so which we can basically obtain, or which we can extract from the SPT even at the required depth. So this is one advantage of SCPT. Disadvantage of SCPT. We cannot extract the sample. Now, what is the advantage of SCPT? So disadvantage is that we cannot extract the sample in case of SCPT, which we can do for SPT. Now, what is the advantage? So the advantage is like that in case of SCPT, we can get the continuous record. Okay, so something like this. The cone tip resistance, suppose this is your QC and this is your depth. So we can have the continuous record along the depth. This is for SCPT. However, for SPT, this SPT is basically done at some regular interval. Suppose 1.5 to 3 meter. Okay. So here we have basically obtained the SPTN value. Here we have obtained. Then here. Then here. So these are basically discrete data points. So this is one advantage of the SCPT, that in case of SCPT we can get the continuous record, but in case of SPT it's not possible. Okay. Okay, so this is something outside of this context. Okay, so now we'll take our next problem, problem 4. So a vane 150 mm height and 80 mm diameter was used to determine the unbrained shear strength of soft clay strata. As you know from the different tests which are basically involved in determining the shear strength of a soil. So you can basically refer to some laboratory tests, something like direct shear, triaxial, and as well as to some field test as well. So here this field test is basically mentioned or talked about, and this field test is nothing but the vane shear test. Okay, so this is nothing but the vane shear test. And do you know about the necessity of this kind of test? Since there are laboratory tests by which we can easily determine the shear strength parameters like C and pi, cohesion and friction angle, then why there is a need for vane shear test, this kind of field test? Because the difficulties associated with sampling. Whenever you will basically test a sample in the lab, first you have to basically take or extract the sample from the field in a very careful manner. So earlier we have basically discussed that for determining the shear strength parameters, you have to utilize or you have to obtain undisturbed soil sample. Now this getting this undisturbed soil sample is very much difficult in case of soft sensitive clay, very soft clay. So whenever you will be trying to extract the sample from the field, there is a much probability or chance that the sample will be disturbed. So that if you still use the sample in the laboratory for determining the shear strength parameters, you will be ending up with some erroneous results. So the actual field condition you will never get. So that's why there is a need for in situ test like vane shear test. So there is no need for sampling. So the difficulties associated with sampling is basically removed with the help of this vane shear test. Okay, so you are directly determining the shear strength parameters in the field condition. Okay, so we'll go further about the procedure by which we can determine the shear strength properties of this kind of clay, soft clay, soft to medium stiff clay, by using vane shear. So now coming to the given data, the dimension of this vane is given. This is 150 mm height and 80 mm diameter. Next, torque applied at failure was 45 Newton meter. Subsequently, the soil gets completely remolded and the remolded soil is sheared at a torque of 17 Newton meter. Calculate the sensitivity of the soil. So here we have to report or we have to answer to this question in terms of sensitivity of the soil. Now what is sensitivity? What is the definition of sensitivity? Okay, so the definition of sensitivity is that sensitivity This is basically the ratio of, so either you can express it in terms of unconfined compression strength. This is for undisturbed soil sample to the remolded soil sample. Okay. Sensitivity is basically giving an idea of lost in strength due to remolding. And this is very obvious. When you will be remolding the soil sample, means you are basically breaking down the original structure. So you will be basically having reduced shear strength as compared to the undisturbed condition. And this ratio, unconfined compressive strength of the undisturbed soil sample to that of remolded soil sample, will give you the sensitivity. So depending on this value, you can state whether the given soil sample is means low sensitive, high sensitive, moderately sensitive, something like that you can say. Okay, again there is a chart or table in the standard textbooks where in one column the sensitivity values are given, and another column the type of sensitivity is described. Okay, so this is not the job for this problem. Here we have to only report the sensitivity of the soil in terms of some numerical value, and that we have to determine with the given data, which is basically obtained by performing vane shear test. Okay, now we will come back to the vane shear test part. So in the vane shear test, basically it's something like that. You can visualize. So this is one blade, then this is one blade, okay, and this is connected by some rod, though my drawing is not good. Okay, so something like that, it's connected, and then it's basically twisted. Okay, so torque is applied. Now what will happen? So it will basically form something cylindrical in shape in the soil, this field, in the field. Okay, so it will basically try to deform the soil. So failure basically will happen at this periphery of this blade and along the ends. Okay, so this is the bottom end and this is the top. So in this way the failure will happen when this torque is basically reaching the limit, or when this torque is basically exceeding the resistance of the given soil mass. Okay, so in that way you can determine the undrained cohesion or unconfined compressive strength of the soil sample or the soil deposit. Now how you can determine this unconfined compressive strength by performing this type of test? So for that, so this is, suppose the assumed shear stress distribution. Okay, so here I have drawn the assumed shear stress distribution along the periphery and at the top and at the bottom. Okay, so this is the assumed one for determining the undrained cohesion. Now this T, this is basically the applied torque. Now whenever this T is basically applied, what will happen? The soil is basically try to resist that torque, and when this applied force or applied moment is basically equal to the resisting moment, so the soil mass is at the limiting state of collapse. So it will basically on the verge of failure. Okay, so when this applied torque is equal to the resisting moment or the moment which is basically offered by the soil mass along this periphery and this top and bottom mass. Okay, so therefore first we have to figure out the resistance. Now what are the resistance involved here? What is the resistance involved here? The resisting force. The resisting force is nothing but pi d h into c. So this is the what is this? Surface area. So as I told earlier that you will get some cylindrical shape, okay, of this vent. So it will deform the soil in some cylindrical pattern. So the surface area of that cylinder is nothing but pi dh, because you know the diameter of the instrument or the equipment and you know the height. So pi d, this is the perimeter, multiplied by h, this is the height. So this will give you the surface area, and this is the mobilized cohesion, okay, at failure. This is the mobilized cohesion, that is nothing but the undrained cohesion of the soil. So this will give you some resistance to the applied torque. So this is one component only. So in addition to that, you will be having another component, and this is nothing but from the bottom and top ends. Okay, so for that you have to go for some integration. How? So 2 pi r dr c. So this will be the resistance offered from the top end and the bottom end. Now how it's coming? How it's coming? 2 pi r dr cu. This 2 is nothing but for both the ends. One is for top end and another one is for bottom end. So that's why this is 2. Now inside this 2 pi r dr, and what should be the limit? The limit should be in between 0 to d by 2. Now how this is coming? Because this is coming from this concept. If you consider some annular ring, okay, so this is the plan view or top view I am drawing. So this is suppose the center. So this is your r and this is your dr. So again the perimeter would be 2 pi r multiplied by this thickness dr, and you have to integrate, because this whole plan area is basically consist of summation of the small annular rings. So integrating all those will give you the total resistance at the top and the bottom. Okay, so in this way you will get the resisting force. Now this is force and this is moment, something torque applied. So you have to take the resisting moment about the center. Okay, so now I will determine the resisting moment about the center. So therefore what you will get? Pi dh cu d by 2 plus 2 0 d by 2 2 pi r dr cu multiplied by r, and you have to equate these values with this t for the limiting stability or for the failure condition. Okay, so we'll equate. So t is nothing but pi d square h by 2 cu plus 4 0 to d by 2 pi 4 pi cu, and here r square dr. So obviously you will get pi d square h mu by 2, and here you will get pi pi dq cu. Here it will be 8, and here it will be 4, and here it will be 8. So 3, so then 3 8 6. Okay, so this you will be getting, okay, after integration. So therefore this cu would be nothing but t what you can write in the final form. So it would be pi d square h by 2 plus dq by. Okay, I hope you will also get this expression for determining the undrained position of the soil by using wind shear test. Okay, so here basically we are taking pi common. Okay, d square h by 2 plus dq by 6, and cu we are taking in the left hand side. So this way you can utilize the dimension of the wind shear, means the wind shear equipment and the applied torque, and you can easily get the undrained position. Okay, now this is not the required solution. So what we have to report? We have to report the sensitivity, and as you know that this unconfined compression strength is nothing but 2 times cu. Okay, so this is from the unconfined compressive strength of soil. Again, this is from the shear strength concept. So therefore whatever will be the ratio of undrained cohesion, that will be the ratio of unconfined compressive strength, and it will give you the sensitivity. So therefore the determination of the cu is very much essential for getting the sensitivity for both the conditions, undisturbed and remolded. Now we will basically calculate one by one. So for the undisturbed part, this cu undisturbed, it is basically T1 by this pi d square h by 2 plus dq by 6. And for the remolded part, u remolded, it will be suppose T2 divided by, because the dimension of the equipment is not changing, it's constant, it remains similar, the same equipment you are using. Okay, so only the torque value is changing. Why? Because for failing or shearing undisturbed sample, you need to apply more torque as compared to remolded condition. So that's why you are ending up with 2 torque values, T1 and T2. So easily you can get the sensitivity value as this sensitivity simply would be torque 1 by torque 2, because this denominator is constant. So this part divided by this part, so this denominator in both the cases will cancel out. So the remaining part would be T1 by T2. So therefore 45 by 17. So 45 divided by 17, so it will be 2.65, and this would be the. Okay, so therefore as you can see, if you know the expression of undrained cohesion with the applied torque and the dimension of the wind shear equipment, there is no need to derive this part. Okay, so this is for your understanding only. So you can easily calculate the sensitivity as the ratio of the applied this values of applied torque. Okay, ratio of the 2 torques applied. First one is for the undrained condition, and the next one is for the remolded condition. Is it okay? Okay. Okay. Now please consider this problem 5. So problem 5 is about a seismic refraction test was conducted on a multi-layered soil deposit. The velocities of the first and second layers were found to be 550 meter per second and 1445 meter per second respectively. Determine the thickness of the first layer. Given intercept time at x equals to 0, this T0 value is 10 to the power minus 2 seconds. Now to answer this problem, you have to first understand the philosophy which is basically involved in this kind of seismic refraction test. Okay, and this test is basically this test falls under the category of which kind of test? Geophysical exploration, already mentioned earlier. Okay, so apart from this seismic refraction, there are two more tests by which you can also basically conduct this geophysical exploration program, which are seismic reflection and seismic cross-hole. Now seismic reflection test is having some demerits or limitations and which can be ruled out by this seismic refraction test. Okay, so in today's session we will be confining ourselves only to the case of seismic refraction test. Now what is the philosophy for conducting this kind of seismic refraction test? The philosophy is that suppose this is a multi-layered soil deposit. So this is okay. Suppose I am talking about only 2-layer elastic half phase. Okay. And this is the ground surface. Now, according to the principle of seismic refraction, there would be a source and a number of receivers, including one receiver at the source itself. Now, what do you mean by source and what do you mean by receiver? Source in the sense you have to generate some stress waves in this medium. Now what kind of stress waves? Suppose shear wave, primary wave. Now how you can generate? By using some hammer or some small explosive. Okay, so that's why this is called source and these all are receivers. Okay, so series of receivers, and this is commonly known as geophones. Now when you will generate the stress waves, what will happen? Now immediately after generating this stress waves, some energy will basically travel directly, so in this fashion, to reach this receiver, series of receivers, and some wave will basically try to travel downward, so in this fashion. Now as soon as it will basically encounter some boundary, so this is the interface or boundary between two layers. So obviously the density of these two layers will be different, and since the density of these two layers are different, so velocity will be different. So that's why suppose the velocity of the upper layer is v1 and the lower layer is v2. So some of this wave or stress wave or energy will basically try to reflect in the upper layer, some will try to refract in the lower layer, and some already is basically going directly from the source to receiver. So these two conditions can happen at the boundary. So some part will be reflected and some part will be refracted at the boundary. Now there is a concept of critical incidence, and this is as per Snell's law. Now what is that law? V1 by V2 equals to sin theta 1 by sin theta 2. Now what is V1, V2, theta 1, theta 2? So v1, v2 are the velocities of the stress wave in the upper layer and the lower layer respectively, whereas theta 1, this is the incidence angle. So this angle is known as theta 1, and then when it is refracted, so this angle is theta. So this is the relationship between these two angles and the two velocities as per Snell. Now, based on this Snell's law, there will be a critical angle for theta 2. So theta 2, if the theta 2 value is 90 degree, so then the seismic wave, this stress wave will be critically refracted. That means it will travel parallel to the boundary. So this is this angle then known as critical incidence angle, theta I. Okay, theta IC or theta I or theta C, whatever you can take. So there is a critical incidence angle for which this refracted wave will basically move or travel parallel to the boundary with a velocity of v. So where the stress wave is basically travel or moving with a velocity of v1, that is the velocity of the upper layer, and here the stress wave is basically moving or traveling parallel to the boundary with the velocity of the lower layer. And there is another principle which is called Huygens principle. Okay, so as per this principle, any point in this wave front can act as source of disturbance. So therefore, there is a chance that this wave can refract it back to the upper layer and with an angle of 90 degree minus IC. Okay, so this is, you can take IC. Okay, so I think I have used this notation only. So this is I1 and I. Though whatever notation you can use. So there is a direct wave which is basically traveling over the shortest path, and there is a refracted wave. And how this refracted wave you are basically getting? So first the stress wave will basically go below, or it will travel below with a velocity of v1, then it will be critically refracted at the boundary between two layers, then it will basically move parallel to the two layers, and after traveling some distance it will be again critically refracted back to the upper layer with an inclination of 90 degree minus IC. So therefore, all these receivers, there is a chance that all these receivers will basically report or will be having both these direct waves and the refracted waves. Now, these receivers can record the fast arrival time. Means either the direct wave basically can arrive fast, or this critically refracted wave can arrive fast. So any of these two, it will basically record in terms of fast arrival. Okay, so whatever or means whatever wave will basically arrive fast, so this receiver will basically record the time that this wave there is no ambiguity that whether this direct wave is basically arriving fast or the critically refracted wave. Now earlier in the seismic reflection test, so this was the limitation, or this was the difficulty, that which wave is basically coming fast. So that was the difficulty, and this difficulty is basically ruled out in this test, that there is no need to consider which wave is basically arriving first. Only you have to record the time, whatever wave it may be, either direct or the critically refracted. Now we'll basically see when and how direct wave will basically arrive first and the critical refracted wave will arrive first. Okay, so if you consider some distance, suppose xc, this is known as the critical distance. Now all the receivers which are basically located below this distance, the direct trace wave will basically arrive first, and all the receivers which are basically located beyond this critical distance, the critically refracted waves will basically arrive first. Okay, so now this xc, determination of xc, is therefore very much essential. This is known as critical distance. Okay, now another point in this context is that this kind of test is only valid or will give you feasible result if the velocities will basically increase downward. That means v2 should be greater than v1. Otherwise, you will not get the reasonable result. So you may come across erroneous result also. Why this condition needs to be satisfied for this kind of test, seismic diffraction test? Because as per the Snell's law, if you consider this value, this v2 is less than v1, then what will happen? This refraction will not be critical. So instead of being critically refracted, it will basically refract in this fashion. So it will basically come closer to the normal, to the boundary. Okay, since v2 now is less than v1, so obviously this i2 should be less than i1. So therefore it will be refracted in this fashion. It will basically refracted near the perpendicular to this boundary. So therefore this condition you should keep in mind. Okay, v2 greater than v1. So it's suitable, this test is suitable only when the velocity is basically increasing in the downward direction. That means the lower layer should be having a higher velocity as compared to the upper layer, and it is basically natural, quite obvious in the natural geological formation. So as you go downward, you will be having more density, so therefore you will be having more velocity. Okay, so now coming to the calculation part, what you have to do, you have to basically this from the geophone. Okay, so let me draw it here only. That from these geophones you will basically having the travel time of the fast wave, the wave which is basically arriving fast. Now if you draw, so this is the distance from the source, and this is the time of fast arrival. Okay. Now if you plot, then the behavior, the shape would be like this. Okay, so this is for two layers only. If you extend further, suppose you are having 3-layer deposit, then something like, something like this you will get. Okay, so the slope of these lines are not equal. Suppose this is one slope, this is another slope, and this is another. Now can you please identify the slopes? What is the physical significance of the slopes, the gradients of this line? The significance of the gradients of these lines are that it is nothing but the reciprocal of the respected wave layer velocity. Okay, so for the first one, it is basically the reciprocal of the velocity of the first layer. For the second case, it is the reciprocal of the second layer velocity, and similarly this is the reciprocal of the third layer velocity, because this is time upon distance, and distance upon time, this is the velocity. Definition of velocity: distance divided by time. So here we are basically defining this gradient as time by distance. So in each case, this line will define the reciprocal of the respective layer velocity. Okay, and if you suppose for this problem this third layer is not there, only two layers, so if you extrapolate, if you extend, so this is the intercept time t0 at x equals to 0, and this information is given to this problem. P0 is 10 to the power minus 2 seconds, and V1, V2 are also given to you as 550 meter per second and 1445 meter per second. So this type of data, this kind of plot, you can easily get after conducting this kind of seismic refraction test, and you can easily identify the variation in the gradient, and accordingly you can define the gradient, and you can relate this gradient with the respective layer velocity. Okay, however, this kind of data is not given to us like this time of fast arrival versus distance. Rather, the velocities are directly given to you, the velocity of first layer and velocity of the second layer, and as expected that second layer velocity is more than first layer velocity. Okay, so for suitability of this kind of test, seismic refraction. Now what we will do, we'll basically take the help of some trigonometric concept. Okay, so first of all, for direct wave, for direct space wave, what is the time of travel? So the time of travel, suppose for the receiver is located from the source at a distance of x. Now what will be the time of travel for the direct wave? So the direct wave is basically traveling in this way. So from H to R along this straight line. Now what will be the time of travel for this direct space wave? It will be simply distance upon velocity, na? So the distance is x, and what is about the velocity? The velocity is velocity of the first layer only, so v1. So this is the time of travel for direct wave. Now for refracted wave, critically refracted wave, what would be the time of travel? So the time of travel would be, first of all, the refracted wave has to cover this distance, and this distance is nothing but h upon cos IC. This is from the simple geometry, because IC is the incidence angle, critical incidence angle, and the height of the first layer we are assuming it as h. So therefore this would be h upon cos IC. So this is the distance divided by velocity. Again it would be v1. Why v1? Because here the refracted wave is basically traveling with the velocity of the first layer only. Okay, now coming to this part, second part, because refracted wave is having three parts. So this is the first part, now this is the second part. So for second part, the distance the refracted wave is traveling is x minus twice h tan IC. Now how this is coming? Because this is the distance x, and this distance you can easily determine. Similarly, this distance you can easily determine. So twice of this distance you have to subtract from the total distance between the source and receiver. Then only you can get the distance of traveling of the critically refracted wave along the boundaries between the, parallel to the boundaries between the two layers. Okay, I hope you may get this point. So x minus 2h tan IC. Now in this case the velocity would be v2. Distance upon velocity, that will give you the time, but in this case the refracted wave is basically moving with the velocity of the lower layer, that means v2. And finally the third part, again it will be h by cos IC v, that means 2h by cos IC v1 or v1 cos IC plus x minus 2h tan IC divided by. Okay, so this is the time of travel for the critically refracted wave. Now this expression we can further simplify. How we can simplify? Now based on Snell's law, as we have already discussed. So v1 divided by v2, it would be sin IC divided by how much? Sin 90. So this angle is 90. So therefore sin IC. So v1 by v2, it is basically sin IC, and again this cos IC and tan IC we can represent as 1 minus sin square IC and tan IC sin IC divided by cos IC. So therefore wherever you will basically get this cos IC, tan IC, you can basically substitute this value or values with or in terms of v1 and v2. Okay, so after modifying we can, okay, here I am mentioning as TD and here TR. D indicates direct and R indicates refracted. So therefore TR you will get it as x, I am writing down the final expression only, x upon v2 plus 2h multiplied by 1 minus v1 square minus 1 by v1 square minus 1 upon v2 square. So this is the time of travel for the refracted wave in terms of thickness, distance and the velocities of the two layers. Okay, since we have substituted the values of this represent the values of incidence angle in terms of velocities. So this is the way. So this is nothing but the simplification, only the algebraic manipulation of this expression. Okay, so please do at your own this part. Now as you can see that at x equals to 0, this TR becomes T0. So at x equals to 0, this TR, this is T0 and this is nothing but 2h 1 divided by v1 square and v2 square. Okay, so again this part indicate direct wave and this part reflected, something like that. So 2h 1 divided by v1 square minus 1 divided by v2 square. Now it becomes very easy to determine the thickness h. So to determine the thickness h, just you have to calculate in this fashion: 1 divided by v1 square minus 1 divided by. Okay, so now we'll just simply substitute the values. So 10 to the power minus 2 divided by 2, 1 divided by how much? The velocity of first layer is 550 square minus 1 divided by 1 h, and this would be, I think, 10 to the power minus 2 divided by 2.97 so 2.97 meter, so almost 8. Okay, so this is the way by which we can determine the thickness of the upper layer, and similarly we can basically extrapolate this concept for multi-layers also. So for that we need to know the velocities of all the layers. So right now we are basically dealing with 2-layer soil deposit, so that's how we are having the velocities, 2 velocities for this layer 1 and layer 2, and we can determine the thickness of upper layer only. Okay, now we have already addressed the problem 5, so we have determined the thickness of the first layer. Now still we'll basically go beyond this concept, so we'll try to determine the critical distance. Now what is the concept of critical distance? So critical distance is the distance at which both the waves basically arrive at the same time. Okay, so as you can see this point, so this is your xc. So at xc, direct wave and refracted wave, both the waves are basically arriving exactly at the same time, and before this, below this xc, only direct wave will basically arrive first, and after or beyond this distance, refracted wave will arrive first, as we have basically discussed earlier. So how we can determine this xc? It's very easy. So just you have to equate this td with tr, because at xc td and tr will be same. So you have to equate, so at xc this td and tr will become 1. Therefore xc divided by v1 would be xc divided by v2 plus 2h1 divided by v1 square minus 1 divided by v2 square. Just let me check it once. Okay, this would be the final expression after equating the time of travel for direct wave and time of travel of refracted wave at the critical distance. Now you know v1, you know v2, and the thickness of the upper layer as well. So therefore it becomes very easy to calculate the xc from this expression. So if you substitute the values, appropriate values in this expression, you will ending up with this xc as, so how much I have got? I think I didn't calculate yet. Okay, so I am basically leaving up to you, so please calculate. So this is one homework. So determine xc, the critical distance at which both the direct and refracted waves arrive exactly at the same time. Okay, so any doubts? Okay, if not, then we are having only one problem for this session, then we'll be winding up. Okay, so the final or last problem for this session is we have to basically state true or false. There are 5 statements, and we can easily answer this question, because so far we are having the knowledge about all these statements. Okay, so we'll basically consider these statements one by one. The first statement is dilatancy correction of SPT n value is done for clay soils. Is it true or false? For clay soils, dilatancy correction of SPTN value is required. Or in other words, for which kind of soil dilatancy correction is required? So at the very beginning of this session, we have already discussed about this. Is it true or false? Okay, so it's false. Okay, so why? Please go back to problem 1, because in problem 1 we have already discussed why dilatancy correction is required. So dilatancy correction is required only when the soil is fully saturated and fine sand, and the corrected SPT value after overburden correction is greater than 15. So therefore, for clay soils, there is no need to go for dilatancy correction. Okay. Now coming to second statement, the sample obtained by a split spoon sampler is an undisturbed sample. Now this is somehow related to the parameters based on which we can say or we can conclude whether this sampler will yield disturbed or undisturbed sample. So what parameter you need to figure out for drawing this conclusion whether this sampler, a given sampler, will yield undisturbed or disturbed sample? What parameter you need to calculate or you need to consider? Okay, so this is nothing but the area ratio. And it is the ratio of outer diameter square minus inner diameter square divided by I hope inner diameter square. Now for a split spoon sampler, this outer diameter is I hope 50.8 millimeter square, then inner diameter is 34.9, and then the inner diameter is 34.9. Okay, so this all are in mm. Okay, so therefore if you calculate, then this value would become, so 50.8 minus 34.9 square by divided by 34.9 square. So something 112%. If you calculate, then the area ratio you will get for a split spoon sampler is 112%. Now what is the condition or criteria for getting an undisturbed sample from this kind of sampler? What is the maximum upper limit? Because increasing the area ratio will basically indicate disturbance in the extracted sample. So if you have more area ratio, so you will be having higher disturbance. Now there is a limit for getting undisturbed sample from this kind of sample. Now what is that limit? And again, that limit is basically dependent on the type of soil. Now in general, this limit is 10%, so it should be less than 10%. So anyhow, as you can see, this is for undisturbed, for extracting undisturbed sample. So since the area ratio for this kind of a split spoon sampler is 112% and it is much more than 10%, so you will never expect undisturbed soil sample from this kind of sampler. Okay, so again this statement is false. Okay, now coming to the third statement, seismic refraction method can only be used if the wave velocity in the lower layer is greater than that in the upper layer. Just now we have discussed seismic refraction method can only be used if the wave velocity in the lower layer is greater than that in the upper layer. You should answer this question. If you don't feel comfortable in the microphone, then you can use the chat box also. Okay, so this is the condition already we have discussed, that for this test V2 should be greater than V1. This indicates that the lower layer velocity should be greater than upper layer velocity for this kind of seismic refraction test, feasibility of this kind of test. Okay, so obviously this statement is true. Now, coming to fourth statement, the CPT test is performed in borehole. Is it true or false? CPT test is performed in borehole. Is there any necessity for borehole in for this CPT test, or without borehole it can be conducted or performed? What is your answer? Is there any necessity of borehole? Okay. So if you follow the procedure which is involved for performing CPT test, you can easily understand that there is no need for borehole in conducting CPT test. Therefore, this statement is also not true. Okay. Now the final statement, disturbed samples can be used for shear strength test. This is also discussed in the beginning of this session. What kind of samples are suitable for what kind of test, or the soil parameters. So for shear strength parameters, for determining or obtaining the shear strength parameters, which kind of samples you need to use, disturbed or undisturbed? Okay. So undisturbed samples you need to use for obtaining the shear strength parameters. So that's why this is also okay. So in this way, we have answered all the statements which are involved in this problem. So now we'll end this session by taking one homework problem, and this homework problem is related to pressure meter test. Okay. The pressure meter test was performed in a homogeneous soil deposit. The volume of the measuring cell was 535 cc. The in situ total horizontal stress was found to be 45 kPa, and pressure at just the beginning of the plastic zone was 355 kPa. The volume of the cavity in the original condition is 587 ml, and volume at the end of pseudoelastic zone 723 ml. Poisson's ratio of the soil is 0.35. Find the pressure meter modulus in Newton per mm square. Okay, so these are the data which are basically related to this pressure meter test, and you have to finally report the pressure meter modulus in Newton per mm square. So for that you need to know about the methodologies or the philosophy behind this kind of test, and how to utilize this data to get the pressure meter modulus. Okay, so first of all, this is the schematic for pressure meter test. So this is one pre-bored hole. Now in this pre-bored hole, one measuring cell is there, two guard cells are there. These guard cells are for minimizing the boundary conditions, and this measuring cell is basically connected to some gas or water line. Now, as you know, the methodology of this kind of test, that this measuring cell is basically pressed against the borehole wall. Okay, so it is basically pressed against the borehole wall, and due to that, this adjacent soil mass will basically deform. The deformation of the adjacent soil mass will basically take place due to this pressing by the measuring cell. Now, if you basically take a record of this pressure versus volume deformation or the total cavity volume, so you will be basically getting this kind of plot. Okay, so in this plot, three zones are clearly marked: zone 1, zone 2, zone 3. So zone 1 represents the reloading phase, zone 2 the pseudoelastic, and zone 3 is the elastic. Now the data corresponds to, now all this data corresponds to the pseudoelastic part. The in situ horizontal stress was found to be 45 kPa. Now what is that stress in this figure? So this is the in situ horizontal stress, 45 kPa. Okay, then the pressure at just the beginning of the plastic zone, PA, 355 kPa. So that means this value, 355 kPa. Okay, so this is the ending of pseudoelastic zone and beginning of the plastic zone, zone 3. Then the volume of the measuring cell was 535 cc. So this V0, this is given 535. Okay, so this is in cc. Then the volume of the cavity in original condition, 587 ml. That means V0 plus small v0. So this is in the original condition, so 587. And lastly, volume at the end of pseudoelastic zone. That means capital V0 plus small va. This is 723. So these are the data which basically fit into this graph. So PA, P0, capital V0 plus small v0, and capital V0 plus small va. Now what is pressure meter modulus? Now this pressure meter modulus is basically given by Maynard. So this is also known as Maynard's modulus, and this is based on basically the theory of expansion of an infinitely thick cylinder. Now how you can get this pressure meter modulus? So you can get this pressure meter modulus by this expression, EP equals to 2 times 1 plus mu, then capital V0 plus small vm multiplied by delta P by delta. And if you see very carefully, all these data are with you. Mu, this is the Poisson's ratio of the soil, 0.35. Capital V0, this is the volume of the measuring cell, 535 cc or ml. Then Vm, this is nothing but the average value of the initial and the final condition of the pseudoelastic zone. The average value, small v0 plus small vf by 2. And then delta P, this is nothing but Pf minus P0. This is the difference between pressure at just the beginning of the plastic zone and the in situ horizontal stress. And this is given as, this Pf is given as 355 kPa and P0 is given as 45 kPa. Okay, and coming to delta V, this is again small vf minus small v0, and this small vf small v0 you can easily calculate because capital V0 plus small v0 is given as 587. So if you subtract the capital V0 from this part, you will be getting the small v0. Similarly, if you subtract the capital V0 from this part, so you will be getting the small vf. So if you know small v0 small vf, you can easily determine the delta V, that is change in volume for this zone. Okay, something this type of, this is delta P and this is delta V. Okay, and this is the average one, V0 plus small v0 plus small v. Now if you substitute these values in this expression, you should get the pressure meter modulus. Again, this expression is given by Maynard, and this modulus is also known as Maynard's modulus, and this is based on theory of expansion of an infinitely thick cylinder. Okay, those who are interested, please go through them. So this is all about the homework. So I will request all of you, please try at your home and let me know if you face any difficulties in the upcoming session. Okay, so this is from my side. Again, the next session will be held on next Sunday, 13th August 2023 for the same timing slot, that is 5 p.m. to 7 p.m. Now I will wait for some time. So if you have still any problems, you can feel free and ask me. Otherwise, I will end this session here. So thank you for joining this session, and I will expect that you will also join in the subsequent sessions also.